Welcome to the Explainer. Today, we are going to tackle motion itself. Seriously. By the time we're done here, you're going to have this amazing mental toolkit to understand and even predict how anything moves. Think about it. A thrown ball, a speeding car, you name it.
All right, so here's our game plan. We're going to start with the absolute basics, the language of motion. Then we'll jump into the super important idea of acceleration. After that, we'll unlock the 3 key equations that basically run the show. Then we'll see how gravity, our old friend, fits into all this. And finally, we'll put it all together to figure out projectile motion. It's going to be awesome. Okay, first things first, the language of motion. Look, before we can even touch any of the cool equations, we all need to be on the same page. We have to agree on what words like distance and speed really mean. Because in physics, words aren't just words, they are super precise.
So, let me ask you something. You probably use the words distance and displacement all the time, right? And maybe you even use them interchangeably. But let me tell you, in the world of physics, oh man, the difference between them is everything.
This picture just nails it. See that long, winding path? That's your distance. It's every single step you took, the whole journey. But displacement? That's totally different. It's just that straight line from point A to point B. It's the shortcut. It doesn't care how you got there, just where you started and where you ended up. And this difference is so crucial. Think about it like this. Speed is just what your speedometer says. It's just a number. But velocity is speed plus direction. It cares which way you're pointing. So imagine you run a full lap on a track and end up right back where you started. You definitely had a speed, right? You were moving, but your average velocity is 0. Why? Because your displacement, your start and end point, is 0. You went nowhere. So how do we show this in the math? Well, take a close look at those little arrows over the letters for velocity and displacement. That's not just for looks. In physics, that tiny arrow is a huge deal. It's a signal that says, hey, this isn't just a number, this is a vector. And a vector is just a fancy word for something that has both a size and a direction. Simple as that.
Okay, but let's be real. In the actual world, things almost never move at a perfectly constant velocity. I mean, think about it. We're always speeding up, slowing down, turning corners. Life is full of change, and that change in motion brings us to our next huge concept, acceleration.
Now, when you hear acceleration, you probably think flooring it, right? Hitting the gas pedal. But it's so much more than that. Hitting the brakes, that's acceleration too, just negative. And get this, even taking a turn at a perfectly steady speed is also acceleration. Why? Because your direction is changing, which means your velocity is changing. And here it is, the formula at the heart of it all. Acceleration is just the change in velocity divided by the change in time. Now, that unit, meters per second squared, I know it sounds a little weird, but all it really means is this. How much speed, in meters per second, are you gaining or losing for every single second that you're accelerating? See? Not so scary.
So, here's an easy way to think about it. If your final velocity, v, is bigger than your starting velocity, u, well, your acceleration is positive. You sped up. But if your final velocity is less than where you started, then your acceleration is negative. You slowed down. We call that deceleration.
All right, now we get to the really good stuff, the absolute core of kinematics. We're talking about 3 incredibly powerful equations that, and I'm not kidding, let us predict the future. Well, as long as the acceleration is constant anyway. Seriously, think of these as your new physics superpowers. With these 3 equations, if you know just 3 pieces of the puzzle, say your initial speed, how much you're accelerating, and for how long, you can figure out all the rest. You can find your final speed, how far you traveled, everything.
Solving a kinematics problem is kind of like being a detective. First, you line up all your clues. Those are your knowns. Then you identify your target, your suspect. That's the unknown you're trying to find. And finally, you pick the right tool from your toolkit, the perfect equation to crack the case.
Okay, let's see this in action. Imagine a car. It speeds up from 20 to 30 meters per second. And it does that over a distance of 100 meters. So what do we know? We have our initial speed, u, our final speed, v, and the distance, s. What are we looking for? The acceleration, a. So we look at our 3 equations and, aha, the third one connects all those pieces. We just plug in the numbers, do a little bit of algebra to solve for a, and we get our answer, 2.5 meters per second squared. And see, once we have that acceleration, everything else gets easier. Now we can grab that first equation, the really simple one, to figure out how long this all took. We just rearrange it a tiny bit, plug in the speeds and the acceleration we just found, and boom! The answer is 4 seconds. See how it all connects?
So we've built this amazing toolkit. Now, let's use it on the one accelerator that affects pretty much everything in our lives: gravity.
And this is the beautiful part. We don't need to learn a whole new set of rules. For anything falling near the Earth, as long as we can ignore air resistance for a moment, the acceleration is always the same. It's a constant. We give it its own special letter, G, for gravity, and we just slot it right into those same 3 equations we already mastered.
And it gets even better. If you just drop something from a standstill, what's its initial velocity? It's 0, right? And that makes the math even simpler. It gives us these really elegant little shortcuts to figure out how fast something will be going when it hits the ground and how long it'll take to fall just by knowing the height it was dropped from. Okay, this is it, the grand finale. We're about to combine everything we've learned to finally understand that beautiful, graceful arc of a projectile. We're talking about everything from a thrown baseball to a cannonball soaring through the air.
So, what's the secret to figuring out projectile motion? It's actually really clever. You don't try to solve it all at once. You split it into 2 separate, much simpler problems. You look at the horizontal motion and the vertical motion completely independently. Horizontally, there's basically no acceleration, it's easy. And vertically, well, that's just a freefall problem, exactly like the ones we just looked at, all thanks to gravity.
All right, listen up, because this next idea, this is the absolute key. This is the single most important concept for understanding projectiles. If you get this one thing, everything else just clicks into place. You ready? Here it is. Gravity doesn't care how fast you're moving sideways, and objects' up and down motion is completely 100% independent of its side-to-side motion.
And if you don't believe me, look at the proof right here in the math. Check out this formula for the time of flight. Does that look familiar? It should. It's the exact same equation we used for an object that we just dropped straight down. Now look closely. What's missing? The horizontal speed. It's nowhere in the equation. That means the time something spends in the air depends only on the height it started from, not how fast it was shot sideways. So that brings us to one final classic thought experiment. Imagine you're standing on a cliff. You have 2 bullets. You drop one straight down, and at the exact same time, you fire the other one horizontally from a gun. Which one hits the ground first? Based on everything we've just covered, you now have all the tools you need to figure that out.